thank you for your participation. So I would like to present just one result, or complete result, and the title concept is the inversion of the two data fund transform. Short about the report, summary. I am sure you are familiar with the classical fund transform. That maps a function defined on the unit sphere to its integrals over great circles. Obviously, for an odd function with respect to the center of the sphere, of course, we get 0, so it is natural to consider the transform in the space of even functions defined on the sphere. And it is well known that in this space the transform is invertible and the inversion formula is known, of course. But the problem arises. Find an additional condition that allows us to reconstruct a node function with respect to the center of the sphere. And in this report, an additional condition is found, which is a liquid function transform to reconstruct a node function, and the injected so-called two data function transform is considered. The transform consists of two parts. The classical function transform to invert uneven functions, and the weighted function transform to invert the odd functions. Also, an inversion formula for the transform is obtained. Such inversions have theoretical significance in many areas of mathematics, for example, in integral geometry, in convex geometry. By the way, the inversion of the cosine transform, which plays a fundamental role in integral geometry, was obtained by Rafik using the function transform. Recently, I have discovered that the transform is used in magnetic resonance imaging. So let me remind you the function transform about notation. A function on the unit defined on the unit sphere, which we denote by this way, a square. By s omega, we denote the great circle with pole at omega. By this way, f omega phi, we denote the restriction of the function on the circle s omega, the series integral. So we denote them by, I denote them by ff, maybe not so good notation, but ff is the, so ff is the mean of f over the mean of the restriction over the circle s omega. And by definition, the classical function transform takes function f to its integral over great circles. Functions to even continuous function defined on the sphere, and it is well known that the function transform is invertible. I already say. And the inversion formula is known whenever f is even and sufficiently small. Other Fong, as I know, found the inversion using the Abel transform. So there are many generalizations of function transform. A generalization of function transform to an arbitrary dimension is due to Sigismund-Relgason. The shifted function transform, non-geodesic function transform, and several other generations were considered by Quinto, Mark Agranovsky, Boris Rubin, Salman, and many others. So about the problem. So the problem is find a maximum condition to reconstruct a node function that allows us to recover a known function using function transform on the space of all continuous functions defined on the unit sphere. Note that the problem goes back to Pavel Fong. In this paper, printed in 1916, to reconstruct a node function, he considered hemispherical transform on the sphere. The results were extended to high dimensions by Boris Rubin. Introduction to integral geometry. Cambridge bound 1915. Were extended to high dimension by Boris Rubin. He considered so-called two spherical transforms, so-called lambda cosine transform. You see the transform. So he integrates the unknown function multiplied by a scalar product to the power lambda and integrate over whole sphere. He in the first he considered the kernel with even kernel, and in the second transform he considered the same function multiplied by sigma. He considered odd kernel, and he proved that the lambda transform, the lambda cosine transform of odd kernel, the second one, is closely connected with the hemispherical transform. Using the second transform with odd kernel, Boris Rubin found an explicit inversion formula to reconstruct a knot function defined on the sphere via the hemispherical transform. So, via the hemispherical transform. By the way, in case where lambda equals 1, we obtain the classical cosine transform. So our approach to solve the problem, we suggested a new additional condition, another data, which is a weighted Planck transform. The injectivity so-called two-data Planck transform is considered. Both transforms integrate function over great circles on the unit sphere. Hence, this data different from the data considered in the existing solution of the problem. Also, using the consistency method, an iterative inversion formula of the transform is found. The spherical Gaussian transform is a well-known transform. It is a base, mathematical base of new methods, computed thermoacoustic and photoacoustic tomography, which are new set method for tomography. And using that spherical Gaussian transform maps a function defined in the n-dimensional Euclidean sphere to its integrals over all sphere with the centers on a hypersurface that can be plane, that can be sphere, or any surfaces. So, using the consistency method, I was found a new iterative inversion formula for the spherical Radon transform that has the benefit of being local. So by this formula, one can recover unknown function using local data. I presented the result in previous case in OTHA Spring 24, and the article was published recently in German. Inversion of the two data spherical Radon transform with central motion. I tried to use this method, the consistency method, to invert the two data Planck transform. So I consider the following weighted Planck transform. So I need to choose a reference point on each circle. Let me show. So we have a circle, a sphere. This is the gray circle, for example, with pole at omega. This is a north pole. I choose the projection of the north pole onto on the circle s omega, and this point I choose as the reference direction, and denote it by n omega. So hence the direction one can use to determine the direction using the angle with respect to the polar angle, with respect to the reference direction. For a given continuous function, I define the following two weighted Planck transform. So I consider also I consider also the restriction of f onto the sphere s omega multiplied by cosine phi and integrate over the circle. And denote them by Cf. So Cf is the weighted Planck transform. Here we integrate over the circle. Similarly, I consider the second weighted Planck transform multiplied by sinus phi. So we have I define two weighted Planck transform, Cf and Sf. Note that the definition of Cf, respectively Sf, depends, of course, on the north pole because it depends on the reference point. In the case where we consider this transform with respect to another direction, say omega, we will denote it by C omega f, capital omega f. The classical Planck transform does not depend on the North Pole. So let me present the final result, because the topic is not typical for this workshop. So the main result is the following. Let f be a continuous differential function of the first order, can be non-even, any function, and omega is the direction. So the theorem states that the value f omega can be recovered using the two data Planck transform. Of course, here omega we take as North Pole. So knowing these two functions, one can recover the value of the f at the point at the North Pole at the point omega. Now let me present the inversion formula. First of all, we define two sequences of trigonometric polynomials. I denote them by Pn bar and Pn 0. We have some coefficients here, and also we have an algorithm or formula, recurrent formula to calculate all these coefficients recursively. So we have these two sequences of trigonometric polynomials. By the way, we call them standard polynomials because their construction does not depend on f. So they are universal. So here we present a reconstruction formula for Fn. To recover f omega for another direction, just one can choose omega as the North Pole. I use usual spherical coordinates for the direction, nu tau. Here nu is the polar angle and tau is the azimuthal angle. And to recover f omega, we define the following two functions. So we have a transform and weighted function transform CF. We consider its average over azimuthal angle. So consider these integrals and denote them by this way. So this function are average of FF and CF. Now the inversion formula is the following. So let beta 2 FF and CF be the two data function transform, sometimes called function Latin transform of function f. And to recover Fn, we have the following expression, following formula. Here, CF and FF overline are the average of the two data function transform. Pny and Pn0 are our standard polynomials. So we integrate over the segment and consider the limit. By the way, in case when we have and in case when f is an even function, so for even function CF is 0, so this part will disappear and we obtain the reconstruction formula for the even function. In case when f is an odd function, in this case f function transform is 0, so we obtain a reconstruction formula for odd function. So in general case we have this formula. Iterative reconstruction formula to reconstruct the value of f at the point n, at the point on n, North Pole. To recover f for another direction, just one can choose omega as the North Pole. Thus, to reconstruct any function, we have to know function transform, two data function transform, and C omega for all omega, for all directions. It turns out that knowing two weighted functions CF and SF for a fixed direction, for a fixed point, for example, for the North Pole, one can calculate C omega for all directions. For all directions. So we have the following theorem. Let CF and SF be the two weighted function transforms of function f with respect to one point, for example, North Pole. For any other direction, omega, C omega has the following expression. Here, alpha is the following angle. For example, omega is in another direction. Omega is in another direction. So we have the projection of the North Pole on S omega. we consider also the projection of the omega, capital omega onto the circle, and alpha is the angle between these two projections. Thus, we have the following final result that states that let CF and SF be the two weighted transform of function with respect to one point, North Pole, for example, the transform. This transform is invertible in this form. Now let me speak about the approach. First of all, I would like to present the inversion formula in terms of the Fourier coefficient. So I consider the Fourier expansion of the restriction f omega phi by this way as follows. Here, of course, the first element is the Fourier transform. Integral of it's very interesting that the weighted function transform is the first cosine coefficient of the Fourier expansion. Is the first cosine coefficient of the Fourier expansion of the restriction on S omega. For an angular coordinate of the reference direction n omega, of course, we have phi equals 0, and substituting into this expression, we get the following is the expression for the f n omega. So f n omega is the sum of the following series. And for the North Pole, we will have this expression. One can integrate both sides of this expression with respect to azimuthal angle, and finally we obtain this the final inversion. We obtain the inversion formula for Fn, which is the sum of the following series. So to obtain to calculate Fn, we need to calculate all cosine coefficient of the Fourier expansion of the restriction and average them. So our aim is to calculate all cosine coefficient of the restrictions. And to derive this coefficient, I used I call them the consistency. I call it the consistency condition. I mean the following. Let's show what I mean. Let's just show it. What is the consistency method or consistency condition? So with that, we have some function on the sphere, unit sphere maybe. So we consider its all restriction on the great circles. Then let's denote it by f omega phi, of course. And we obtain some family of functions. This family is not an arbitrary family. This family is consistent. For any direction, omega, for example, for any direction, omega, for example, let's consider all circles containing omega. The bundle of circles containing omega. The consistent method is the following. The values of these restrictions on the circles at this point are the same. This is consistency condition. By the way, the inverse statement is also true. Using this simple condition, I derive the partial differential equations for the coefficient an and bn. The coefficient of the restriction Fn on the circle. You see the equation. We do not need to solve this equation because our aim is to calculate the average of coefficients. So one can integrate this expression with this equation with respect to azimuthal angle tau, and finally we obtain system of differential equations for average coefficients. And here we got lucky because it is very simple to derive the average coefficients from the system of differential equations. By the way, we have also the boundary condition here, and for let's go. I suggest the following algorithm. Let's knowing A0, which is the Funk transform, one can easily calculate, taking into account, of course, boundary condition, one can easily calculate A2. Substituting into third equation, one can easily calculate A4. Substituting into the third equation, one can A6 and so on. So by this way, knowing just Fourier transform, one can easily calculate all Fourier coefficients with even indices. So one can calculate even function. One can recover even function. Similarly, knowing A1, which is our weighted Funk transform, one can calculate A3, substituting into the fourth equation A5, and so on. So knowing the weighted Funk transform, easily one can calculate all Fourier coefficients, cosine coefficient, with even with odd indices. That's why so one can recover an odd function. Still to substitute this expression into the inversion formula, and we find our final inversion formula, iterative inversion formula. So using this one, and we find that this. By the way, I have some computational implementation. Let's consider this function, very simple function, cosine curve. Nu is the polar angle. So for the North Pole, we have Fn is equals 1. And let's try to recover Fn using this approach, using our inversion formula. We have to, it's an odd function, so F Fourier transform is 0. For the weighted, Funk transform is 0. For the weighted Funk transform, we obtain the following expression. Also, we use our standard polynomials. Substituting into our expression in inversion formula, we obtain Fn is just 1. So we obtain the exact reconstruction just for the second step. Because cosine curve is orthogonal to functions. So that is all. I just presented one result. I will complete. Thank you.